Scenario B has a couple differences compared to scenario A. So first of all, now we have a decrease in infections. So as days go by, there are fewer active infections as more people get better than contract the coronavirus infection. These are, again, hypothetical numbers to keep things simple for the sake of our math problem. So it's a nice constant rate linear pattern. But hopefully this is something that we would see, is that people heeding warnings and seeing that increasing their socializing and getting together leads to an increase in infections in our area. People would kind of rein it in, which makes it a lot easier if the weather isn't quite as nice as it is lately. We will see. So that's one thing, is infections are going down. And the other one is our rate, you can tell, is a little bit more complicated. It's going down by an average of 3 infections every 2 days. That's just an average. And so if you think about that, 3 over 2, if you simplify that ratio, you can also actually write this one, if you don't like that fraction, you could write this instead of 3 over 2 as 1.5 infections per day. Of course, you can't have half of an infection per day, but remember, this is an average. It averages 1.5 infections per day. So one day maybe it goes down by 4, and another day maybe the infections that are going on go down by 2. Average those out, you get 1.5 infections going down per day. So I chose a few numbers. I just kept going up by 2 days, the first few increments. So I went from 0 to 2 to 4 to 6, because every time 2 days pass, 3 fewer infections are active, and so I just removed 3 each time. And then I chose a few more numbers, so I went out a little bit farther. So remember order of operations. First, you're multiplying by 3 over 2, or 1.5, to get the number of infections that it went down by, and then taking that away from the initial number of infections when things started decreasing, of 45 infections. You can see my calculations there, and just remember again your order of operations. Multiply before subtracting the decrease in infections from 45. You'll know you're doing this right when you graph your points if all of your points land in a straight line, even if you're not using a 2-day increment. So I went up by 4 days a couple times. Those points still land on the same straight line if I was to take a ruler and connect them, because this is a constant rate pattern, also known as linear, and one of the characteristics of that type of pattern is that all the points land in a straight line. Just like that. And again, like before, remember, I only have data for days 0, 2, 4, 6, 10, and 14. Those are just the points that I picked. Remember, once you graph those points, all the points on this line are XY values that make the equation true, or they fit that pattern of starting at 45 and going down by 3 infections every 2 days. So I could pick a number like right here. This would be day 8, where I don't have any data in my table. I didn't make a calculation, but I could use that pattern and say on day 8, 8 would be right there, I could make an estimate of about how many infections there would be on that day. It looks like there'd be around 33 infections currently active on that day, without actually making a calculation or including that point in my data table. So that's what every point on that line means. We're just using a handful of the points in order to display the pattern and establish what that pattern is, help us write an equation, and you can also use it to sort of visualize what's happening to the infections over time. And so we want to do the same thing and use that data table pattern and graph in order to write our equation. So just like the one before, I can find my y-intercept from the value of y when x is 0. So on day 0, total of active infections is 45. So that's my y-intercept. That shows up on my graph way up here, where the line hits the y-axis. And it shows up in my equation as this number that's a constant. It doesn't change. It's not multiplied by anything. No matter how many days down the road I go following this pattern, it started at 45. So I have 45 for my y-intercept. And in slope-intercept form, it's also called the b value. So b in this case would be 45. And like the other one, we could write this equation a little differently if we wanted to, if it fits the scenario a little bit better. If you like to think about starting at 45 and then decreasing or subtracting infections for some number of days, my equation could also look like this. Again, because order of operations, whichever way it's written, you're going to multiply by 3 over 2 first to figure out how many infections the active infections have changed by, and then I'm going to take that away from 45. The other part of our equation, that rate of change, oh, I almost did it again. Don't forget to highlight this in your graph as well. So notice I use blue for the y-intersection everywhere. So the other part of the equation was the rate of change. So there's that 3 infection every 2 days. That's a rate, so that's our rate of change. And it's dropping. So remember what that dropping means is it's going to be a negative rate of change. So I'm subtracting some number from my starting value every couple days for every increase in time. So that shows up as the multiplier that I'm using every time in my calculations, multiplying by 3 over 2 or 1.5. But remember, if you didn't know what the calculation was and you just had the XY pattern or you had a graph, you would also want to be able to find that slope by just comparing your change in Y to your change in X. So that 3 over 2 also shows up here where it goes down by 3 every time the days go up by 2. It happens again here and here. And so notice there's my rise over run, minus 3 over 2 or negative 3 over 2. That's where that slope is coming from. And if my points aren't evenly spaced like that, so when I started counting by going up by 4 days, notice my infections go down by 6 over 4 days. Remember, 6 divided by 4 is equivalent to 3 over 2. I'm just looking at a longer span of time during which a larger number of infections resolved and went away. And so my slope that I would put in my equation would be negative 3 over 2x, or if we're doing this the other way, taking 45 and subtracting 3 over 2 times x. So that's where it shows up in the equation is the multiplier of x. Because when you have a rate, you have to multiply that rate by something to get the actual change. Like if you were riding your bike somewhere and you were going 10 miles per hour to figure out how far you've gone, you multiply 10 miles per hour by some number of hours to get how many miles were covered. The same thing happens with infections per day. Multiply the rate of change in infections per day by some number of days, and you get the total change in infections over that period of days. That slope also shows up in our graph as that stair step between points. So whether you're looking at these stair steps here, so that's going down, going by 2 days each time. My infections are dropping by 3. Or if my points are farther apart, but still on that same line, I'm looking at 4 days, during which the infections went down by 6. So remember, that is an equivalent ratio to negative 3 over 2 is negative 6 over 4.